Yeah, eventually get it all working here. So welcome all, and thank you for coming. Quick question. Who's read this paper? No one's read it? One. You should all read this paper. It's a brilliant piece on the problems that we have in production systems and what causes major outages. So there's many different things. There's a great section in this on testing. What do we think is the #1 cause of production outages of systems? When systems go down, what's the #1 cause? Disks? Human error. That's it. Operator error is what they defined. It is by far the most common cause of problems we have in systems. This also references many other pieces of research in this area. And quite often, this happens typically when a failure occurs in the system, we've got to bring up a backup, another system. And I've got a personal story of this. It happened about 12 years ago where I was running a team, and in the middle of the night, we had a system that failed. And the person who was on duty tried to swap over to the backup system in the middle of the night, and they made a mistake, and they corrupted the system. And they tried to fix it when they're being tired and half asleep at that time in the morning, and they started making things worse and worse and worse, and they didn't call for help as they were in this state, and they kept making even greater mistakes, and eventually it got escalated to the point where other people got involved, and we tried to restore from backups because the primary system was dead. The secondary system had been screwed in trying to set it up, and when we went to backup tape, we had the shock of discovering the backup didn't work either. Twice in my career, I've gone to backup tape, and twice it hasn't worked. It's kind of interesting for that. Now, we had the ability to fail over in this, but it was decided that we would do it manually rather than via some sort of automated process. And what this paper kind of shows is how things feel, but also how humans feel. And we feel as much as our software, actually much more than our software does. So the best thing we can do is we need to have a good practice in place that's well tested that we can do our fail over to another system. And this is kind of why we have clusters. We have clusters so we can have a new machine take over in the event of failure and have that done in a well-tested and automated way. And we often use consensus for this. So you kind of think, what does consensus mean? Well, one of my things I like to do a lot whenever I'm working with any sort of technology is go to a dictionary definition of something, because we're terrible as an industry for doing this. So I kind of look at, well, what does consensus mean? Well, it's a pretty good fit here. It's about having general agreement on something, but the primary definition is actually about unanimous agreement, which is not typically what we're after. It's actually the secondary definition of consensus is what we're typically going for, is we're trying to get a majority or at most a certain percentage of something to agree with something. And that's so that in the event of failure, we can at least choose what we think makes sense. Now, what are we talking about consensus on here? Consensus on what? Well, it can be consensus on a single value, like which is the node that should be up now and alive, which is the best candidate for doing that. It can also just be where are we in some state or some model. So this can be applied to many different things. There's a number of interesting papers and a lot of interesting work. This work goes way back now. So particularly in the 1980s, we had a lot of advances in this area. So people like Leslie Lamport done good work. Well, most people have heard of Paxos. It's kind of become one of the best known things in this area. But there's a lot of simultaneous discovery around this time. So view stamp replication, virtual synchrony, things we're doing with atomic broadcast. So Ken Berman, Barbara Beliskov, lots of other people did some great work in this area. There was something that happened around this period kind of going forward, which is really interesting. It's not the theory that we need to care about quite often, it's the implementation. Some of these approaches were well proven, they were proven to be correct. They fell down because implementations were incredibly difficult, and most people made mistakes trying to do that. So Paxos particularly was notorious for this. Very few people could implement it in a safe way. That spawned an interesting paper that came out 2014 around a thing called Raft, which is a new consensus algorithm. And the point of Raft was to come up with an algorithm so we can do cluster consensus, but do it in a way that's easy to implement and easy to understand. So optimized for the humans, not just optimized for the system. And it makes a number of assumptions in this that makes it much easier. So I'm going to talk a bit about how you can implement this algorithm. But a few years later, there was another variant on this. So a paper was done of where people had tried implementations and what was kind of learned from that. And so there's a lot that can kind of come out of this. We realize that we need to automate systems, particularly to deal with failure. When you want to have high availability, you don't want something being swapped over to backup at 2 o'clock in the morning when people are half asleep and groggy. They'll make mistakes. We want a machine to do that in a well-proven way and do it fast. And particularly the doing it fast becomes something that we need machines for. So what is Raft? I'm going to kind of cover Raft in a nutshell here. So Raft is an algorithm. It's kind of Paxos-like, but it's got some constraints within that. And one of the major constraints it focused on was, let's keep the state space as small as possible, and from there we can reason about it much more. It achieves that by putting all nodes into one of only 3 roles. So you start a system up. All the nodes that are in the system are designated as followers. So they don't know who the leader is yet. You're going to try and resolve who is the leader of a system, and for this they have an election protocol. And around that, what happens is at a given point in the startup, you'll agree that, okay, I want to try and become a candidate, and you'll request votes of the other followers to do that. There's an interesting challenge to that. How do you decide who becomes the candidate? We have no central control to doing this. This is resolved by using randomization and timers. So you set a random timer. After a period of time, one of the potential followers who believes they can be a candidate will propose themselves to become the leader of the cluster. They'll enter the candidate state. They'll request votes of the other followers. If they get a majority, they can then become the leader. So it kind of works in a nice way. If we get a conflict at that point, you could have 2 candidates propose at the same time. We could get a split vote and a failed election. What you do is you just go back and you do it again with another randomization. So eventually it will be resolved. And typically you don't get clashes when the ranges are over a reasonable time period where the range is significantly larger than the round trip time between the machines, and you've got a reasonably random seed that goes into that. That's kind of cool. You've now got a cluster that can run with an elected leader, all working quite nicely. The leader can die at some stage. You go through exactly the same process again. You just elect a new leader from the current list of followers that are still around, and from here we can go forward and progress. We don't have the case of at 2 o'clock in the morning, someone's pager goes off, they've got to go in and they've got to start entering commands into a system and they make a mistake. It can be something that's well tried, well tested. So only 3 roles, 3 interesting states in the system. It's also got 2 RPCs that are defined. One is, how do we deal with the election itself? So we request votes. So once you become a candidate, you can request votes of the followers. And part of the protocol around this is you ask another follower, can I have your vote become a leader? And you provide how much detail you have around your current log. So how much state you currently have. So how up to date are you? If you are more up to date than the follower you're requesting, or at least up to date with the other follower, they can vote for you at that stage. If you're behind the candidate that's proposing, they should not get a positive vote at that stage because they don't have the latest version of state. They should get a negative vote from the follower, and that way they'll fail in their attempt. The idea being is we will get the leader being elected who has the greatest amount of state, or the most recent amount of state available in the cluster from the members that are available at that point in time. That's one of the fundamental differences between ViewStamp replication, Paxos, and Raft. So those others, they allow you to elect a leader where the leader is not ahead of some of the other followers. You then get into a protocol of catching that up. Now, there are certain advantages to that, but there's also a lot of complexity. And in that complexity lies a lot of potential for implementation mistakes that can cause this to be incorrect. Once the election's over, leaders tell the followers to append entries to their log. So they just call each of the followers in turn as they sequence data that's coming in. You add this to your log, and they also, as part of doing that, provide you information on what part of that log you can now process. So the bits that they have received a majority of the cluster saying, I have this appended to my log, that can then be processed by those other members. I'll get into this in a little bit more detail and you'll see it getting worked out. So just 2 RPC calls and 3 roles. That's the kind of core of the algorithm. Nice and simple, actually. It's quite easy to reason about. Much, much easier than dealing with Raft. Interestingly, view stamp replication has become simplified in a very similar way in recent years too. So we're kind of converging towards much more simple algorithms in this space. Taking this approach, we get a bunch of nice safety guarantees, and these have all been formally proven, where we can guarantee that we will only safely elect 1 leader at a time. We will make sure that the leader will only have the latest state. The leader is the only one who can extend other logs. All leaders through the different election cycles will have the logs matching right through history. This is all kind of nice stuff, but the good thing is it's all been formally proven through quite a simple model. So we get these nice features that come out of this. What I find is quite interesting is this paper doesn't talk so much about how this works. But if you read a lot of the other papers, one of the things that really stands out is a lot of this is actually based on a lot of functional theory. So monotonic functions is what's core in a lot of this is we only go forward with elections. So you increment the term every time you do a new election. You add messages to a log, only ever increasing the log. You only ever accrue state. You never go back in history. It makes it much easier to reason about. And when you start understanding some of the fundamentals behind it, you can see how some of the different protocols are related to each other. You can actually even steal some nice ideas in implementation from some and apply them in the other case. And you can reason about it, and you can be pretty certain you can get it reasonably correct. I like to think about it as you basically version all the things. It becomes an important thing to think about state as immutable, and over time you keep increasing that state, but you version everything, and then from there you know what you're dealing with in a given stage. It becomes nice and easy to reason about. So where does Aeron fit into some of this, and kind of like why did we apply it? Well, Aeron is a nice messaging system. It runs pretty fast, well, pretty much faster than anything else that's out there by quite a bit. And people keep asking us, well, can you give us better guarantees for messages arriving? So they want these different delivery guarantees. We keep hearing this over and over again. And the common one is it guaranteed delivery? I hear this from many, many people. Usually someone a bit like this. There's usually some architect in some place, kind of has opinions on how things should be, often hasn't written code in probably 20 or 30 years, maybe didn't even really write much code in the first place, but they demand these features in a product and they don't really know what they're asking for. Like, if anybody wants to sort of look at some of the history of some of these protocols and different things, like, presume everyone's heard of two-phase commit. Does people know that it's been formally proven as incorrect? Like, all the guarantees, like, people read the heuristic section of the papers around that. These people demand this sort of stuff, but they don't know what they're really asking for. It's kind of like, well, what do you need to know around this? Like, I find that what's interesting is why these people behave in a certain ways. They take a need-to-know approach. They hoard information, and they do it with their vendors. They demand a feature of a vendor, thinking that it's going to fit into their world, rather than thinking, what is the overall world and what is the problems we're trying to address? I like to think much more along the lines of, I want guaranteed processing of something, not guaranteed delivery, because the delivery doesn't matter. It's the processing of that message to the event at the end of the day that really matters. If it's delivered more than once, that's fine if what you're delivering to is idempotent, and you can tell that because you've versioned all of the things. There's lots of easier ways of reasoning about stuff. Like, even if you take something that would give you guaranteed delivery, what if you consume it from that and then you go to process it and you crash before you finish processing? It's the guaranteed processing is what really matters. And this sort of thing fits a lot, particularly in the finance world. I spend a good bit of my time in finance, and we build interesting systems, typically in-memory systems. And these in-memory systems have to go particularly fast, and because it's purely in memory, what happens if we switch the machine off? What happens if it crashes? We need to be able to recover things. So how do these sort of systems look? Well, we typically have a number of clients are going to send requests to some service somewhere. Pretty simple. Typically, that service will want to record things to disk so that if we switch it off and switch it on again, we can get back to our current view of state. Bit of a problem with this. What if the disk becomes corrupt? What if the machine bursts into flames? What if a number of really interesting things? So I can give you a real-world example from a few weeks ago where now with MiFID II regulation coming into effect in Europe, people are having to use microsecond timestamps on all orders. It must be applied. So there's some friends of mine were working on a system. They were applying microsecond timestamps to everything. They got hardware to do that. They happen to have one of the highest volume systems in the world, and the clock that they were, and the system they're requesting these timestamps off at that rate was not specified to cope with that. The machine burst into flames because it was worked too hard. So things bursting into flames is really not just a flippant thing. It really happens. I've seen it quite a few times. So having the single service, even if you're logging it to disk, is it really a good approach? We need it on more than one location. And particularly if you want to start looking at hot upgrades. That's another very common thing with likes of trading strategies and people in this space is they want to hot upgrade a system. And you're not going to shut the system down and bring it up again to do that. You want to do stuff like add a new node into a cluster, running some of your new code, getting it to take over and take the old code out of the system. We want to be able to do those sorts of hot deploys. For that, we need to have the state in more than one place. So we'll typically run more than one instance of something. And we tend to split the systems up by having consensus modules to manage the cluster state, run our services themselves, and we're still logging to disk. But we're logging to disk in many locations now. We've got it in memory in many different locations at any given point in time. And ideally, you won't have two of something because in the case of two, you can't really resolve any sort of disputes. And you can't tolerate failures and still have a reliable system. So you need typically a minimum of 3 for this. 3s and 5s is very common for your kind of cluster sizes that we're dealing with it. And the majority will be sort of cluster size divided by 2 plus 1. Now, how do we coordinate this and how do we deal with it? So Todd and I, we spend a lot of time building these sorts of things. So one of the things I feel I should share is we build these things, we offer them out as open source, you all get the benefit from it. So as part of benefiting from it, you should share a little bit in our pain that we have to deal with. And dealing with NIO is a little bit of the pain we often deal with. A kind of interesting question, do servers crash? Yes, I think it's pretty certain they do crash. Now, if you're going to be logging to disk, and if we're going to be even f-syncing to disk, keeping our data, is there anything we still need to worry about? So I'm going to record to disk, I'm going to write to disk, and I'm going to f-sync all of my writes. Is there anything else I need to worry about? Flushing? Well, yeah, you're going to have written it out, and you're going to flush it. Now, if I've got a file, and I'm writing that file to disk, and I'm f-syncing that file to disk, can I lose that file in any other way? What if you have not f-synced the directory? Am I familiar with lost and found? This is where your file is going to end up. Even if you've f-synced that file, you've got to f-sync the directory as well when you create that file in the first place. Try doing this in Java, and we start doing some weird code that looks a bit like this. So I've got this kind of ugly code here at the top. I've got a file channel. I'm going to open the file channel. Note I'm only opening it for the directory, and I'm giving it no options. This isn't in the documentation as a way of using this. And I might get an I/O exception. Well, in fact, if I do that on Windows, I will get an I/O exception, and I won't get an I/O exception on Linux. And then afterwards, if it's not null, I'll call force on it with true to force the metadata as well as the data itself out to disk. This horrible little idiom that I'm applying in these both places is so that I can f-sync my directory to disk, not just my file. Because the Java API has no means of doing this, and we have to do evil things like that to make it work. It would be really nice if we just had a nice simple call, say something like this, like files.force for a directory. And force the metadata as well. That would be kind of nice. We can't have that, but let's face it, we have var now in Java. So we can't have safe directories on disk and make sure our data stays forever through supported things, but we have var. So so we feel good. Let's talk a little bit about performance, and how does performance fit into this? Particularly, let's look at what it means if we design based upon RPC as a way of thinking. So if I've got requests coming in here, and I'm now going to use RPC, remote procedure call, by its very nature is synchronous. Now, we can do certain things with futures and promises and sort of make it a little bit more stretched out, but what happens if we just consider it as basic RPC? Well, request comes into the system. It's going to hit whatever is the designated leader at that point in time. The leader then will need to save it to its own disk. So that's going to take some time. Writing the disk takes some time, especially if you're going to f-sync it. Then the leader has to replicate it to one of its followers. In this case, send it off to another consensus module. That will then have to replicate it to disk at that point, save it down, f-sync it again. Now think about time is now ticking on as we're doing this thing, because it's all happening in serial by doing this. The consensus module then needs to replicate it to another one at that stage, which again has to replicate it to disk, or sync it to disk. This stage, we can actually process it via service. Because you think about it, we now have it on a majority of servers on disk at this point. We have it on the leader, we have it on one of the followers, and I can actually start processing the data at this point. Now, these are going to layer on top of each other over time. Whenever you've responded from that call, the leader can also execute it against its own state machine at that point, and we can start making progress. So we can only consume something within the state machine itself once it's safely on disk on a majority of the cluster members, and now we can go forward. But start thinking about, like, where does concurrency and parallelism come into this? I say, okay, we could have done some of that stuff with futures and promises, but we can't do all of the bits down the disk and all quite as well, and it's nice. So how does things fit together? Now, Dave done an excellent talk yesterday, and one of the points he made in this talk was he's a parallel nerd. I like to correct him. Dave is not a parallel nerd. He's a concurrent nerd. Dave is a single entity who can time slice, but he cannot do the two things at one time that he was talking about. He can split his time among them. And again, like, we mix these terms up an awful lot in our industry. I like how John Gustafsson actually splits these apart. And these are distinct, and we shouldn't try to interleave them. So think of parallel as the opposite of serial. Concurrent is the opposite of sequential. Those are quite distinctly different. He actually talks about in many of his papers, he will not use the terms concurrent and parallel in the same paper because of the confusion it causes around that. Again, like us as an industry, sort of not thinking about stuff. Actually, I really like the third point, and I'll get into how the benefits of some of this coming. Thinking in vectors is a really powerful way of dealing with so many problems. Simple way of summing that up is batching is really, really cool. And I'll show you some examples of why it's really cool in a second. So we can get much more throughput and much lower latency if we start thinking about what can we do in parallel, consider the concurrency, but also how do we get things going in vectors. Now, one of the places we can learn a lot from is hardware. A lot of this stuff has been done in hardware for a long, long time, so we can get a lot of inspiration from it. So if I'm going to process instructions inside a CPU, I'm going to do it in a pipeline. And it's because I can use different electronic circuitry for each of the steps of the process. So when you process one of your instructions, it doesn't just happen in a single cycle and it's all over. It's done in a series of steps. So first thing we've got to do is we've got to fetch the memory for the instruction itself. And that instruction then we can then execute. But we can't just execute that instruction, because even if we're on x86, our x86 assembly instructions are high level as far as our processor is concerned. It needs to decode those instructions down into micro-ops, and then it can execute the micro-ops themselves. So that's another step in the process. And then we've got these quite complicated CPUs that are now known as out-of-order speculation engines. And they need to pull things back into order at the end, and they need to write things out to memory. So they've got quite a complicated retirement phase to that. So we end up with these 4 steps. They can subdivide those into even further steps, but we typically have these 4 steps. So imagine my theoretical processor took 1 cycle per step, and I wanted to process 4 different instructions. If I was to do those all in serial, we will end up with 16 cycles to complete it. But If the hardware that can do the fetching starts fetching the next instruction once it's finished, and the decoder starts decoding the next instruction once it's finished the previous one, we can start pipelining these things like that. Now, I can complete my 4 instructions in just 7 cycles. So make use of the pipelining effects. This is a nice way to have concurrency and parallelism working for us in doing this. We look at consensus. We've got a number of steps we've got to deal with. First of all, we've got to order our inputs. We have many different clients sending in requests into the system. If we want to create a log, and that log is going to be deterministic, we have to apply a sequence to that. So we need to order the things that are coming in. We'll then log them to disk, so we kept it for later. We need to transmit it to the other nodes in the system. We can apply a commit protocol so that once we have reached majority of nodes containing those, we can commit those changes into our different state machines, and that's where they get executed. So we pipeline that process. Now, if we can start doing that as a pipeline, we can start getting a much greater throughput in our system. How is some of this going to play out if we look at our example here? So if we look at this system and we start running all of these different components on different threads, and they can communicate in some way that's very cheap for the communication to happen, but also happens completely sequentially and happens concurrently with each other, we can get a lot more going on in here. So what would this look like? Well, if we get a request that comes into our system, it hits the consensus module. If the consensus module can, at the same time, send to all of the other components that are interested, we save a lot of time in going through and processing this. I'll go through the different components of Aeron that lets us do this. Like, we can deal with the writing to disk, the sending to the components, the execution in the state machines. All of this is happening in a pipeline at the same time, and that data is not copied at all. It goes through all of this with single operations for dealing with it. Consensus modules can be responding with positions that they have dealt with up to that point, and that can feed into the data that's going out again for replicating where you can consume in the commit position. This way we can get through things at a much greater rate. And that process repeats. We'll get another request in, we'll just replicate it out, we'll get back the position that's been appended, and from here we can distribute the consensus position that's been commit, and we just have that going as a pipeline. So back again to NIO-pane. What other things do we need to do in this? Well, we're working a lot with binary protocols. We're trying to write this data out to network and to disk, so we're using things like byte buffers a lot. So we'll typically allocate our byte buffers, and we'll start writing some data in here. So here's a simple example of I'm going to put an integer into a byte buffer at a given index. There is a perfectly good API that lets me do this. What's interesting is I can have separate threads doing that because I'm putting by index. So there is no relationship between another thread that's putting something by index to a different location in that buffer, or reading from a different location in that buffer. There's an API that doesn't take the index, that uses the position internally of the class. That is not thread safe, so we can't share and we can't get the parallelism out of that. Now, we often want to put bytes into those buffers as well. So if I want to put an array of bytes into there, I'm going to try and put it in by index to a given position. And if I do that, my ID gives me a red squiggly line, which is quite frustrating. Why have I got a red squiggly line? Well, it turns out we don't have the method implemented to put a byte array in by index or another byte buffer by index, but we do have for lots of other types. This bug has been open since 2004 and is still not fixed. But we now have var, and we can save a little bit of typing, but we can't have things safe on disk, and we can't have things efficient. So how can Aeron help with some of the other stuff? Well, realizing that monotonic functions are key to a lot of the consensus algorithms, one of the parts of it is we agree message index is the thing that's going to increase over time. So I get a new message into the system, I add it in the log, add a new message index. There's a lot of assumptions around that. That means that the log has to know about message enveloping. The transmission protocol has to know about message enveloping. We have coupled a lot of implementations to an implementation. What about if we substitute message index for byte index? It's still a monotonic function. It still goes on over time, but most things don't need to know. So the thing that writes the stuff to disk, does it need to know what's in those bytes? No. It needs to know it's written the bytes to disk, written them safely, and know how far it's got through the stream. When it's replicating to other machines, do they care about which message is in there? No, they don't. They're just transmitting bytes on the network, and they know how many bytes have been transmitted again to which point. It's like consuming within the state machines. Once you've consumed within the state machines, how much of the byte stream have you actually consumed? That's what matters, not the message index itself. We conflate too many concerns together in our designs, and that limits so many things. It limits our implementations. It also limits how we can do batching, how we can do replication, how we can do many other things. So I promised earlier that I would talk about how we do lots of things at the same time. Well, when we're communicating between the different nodes in the system, we can multicast. That's kind of nice, easy way we can replicate to many followers at the same time with a single send. Some networks we can't multicast. So for example, if we're in Amazon, we don't have access to multicast. One of the things that we do is we can simulate multicast by using multi-unicast streams, but from the programming perspective, it's just the same, and we will make all of those links point to point. And because our data structures are immutable data structures and functional in nature, we can share them across the different senders without any additional copying. So we get a lot of the benefits of multicast, but we still use unicast streams. Now here's an interesting one. If I'm going to send from a leader to a follower, the leader needs that data themselves. The leader needs that data to write it down to disk to log. It needs that data to consume it in the state machine. One of the things we have is spy-based subscribers, so they can spy on an outgoing data stream, and without receiving the data back in again, can get access to the bytes. And again, because it's a mutable data structure, they can read it without taking any copies. No cost to that. You're consuming on the other machines. When I'm consuming on the other machine, I've got the byte stream coming in off the network. I need to write it to disk. I need to process it by the consensus module to know how far I've got through it, and I need to process it by the state machine. Again, we receive it into one buffer. That buffer's in shared memory across processes. They're all using exactly the same data structure, the same memory, again, without copying. We can greatly benefit from that. And how do we do that? Well, we use the whole concept of the monotonic functions and the fact that we use counters to bound all of our consumption. Because they're just byte streams, they're not message streams as far as most of the components of the system is concerned. It can just work on that nice and simple, and so it consumes up to those points. We can replicate the data to the state machines, but they don't necessarily need to consume it yet. They consume it based on the commit position that's transmitted by the leader, and that way we don't have to send anything else again. Now, how does this matter for batching? Well, if I've got a piece of work that needs to be done, and it's going to take a unit of time, so it says 100% of time for doing something. If I can do two things in the same operation, like write two things to disk in the same I/O operation, write two things to the network in the same send, receive two things from the network in the same send, I've amortized that cost, where each of them is only taking 50% of the cost, if you look at it from a per item perspective. Look at how the payback curve on this pays back really quickly. The biggest win you get is going from 1 to 2, but you start going to 4, sort of 6, 8, 10. By the time you reach 10, you've got the majority of the payback based on batching. You don't have to batch thousands of things to get the benefits. You get the benefits very, very quickly. But if you design such that you can put things into the batches, you get huge benefits in efficiency. Queuing theory comes into effect here because the service time is now amortized across those things. We get much lower latency, much greater throughput. And we can apply this to lots of things. So our system calls, our network round trips, our disk writes, expensive computations. Think about all of this and apply it. And this is the nice thing, is when you're taking it back to the simplicity of it, it's a byte stream, and we're agreeing byte index rather than message index, it becomes easy to deal with. What other interesting features have we added to this? So timers particularly is an interesting one. I've had to deal with this in a lot of different systems. With these deterministic state machines, everything that comes in that mutates the system must come in as a message. You can't read the clock. You can't go to disk to read anything. It must come in this way to be deterministic. So how people tend to deal with time is they pulse time into these systems. If you want really low granularity of time, that's a lot of messages. It's a big log. How do we get around that? We can do other things inside there, but so we decided to tackle this head on. And one of the things we were able to prove by how the replication works is we were able to replicate the ability to schedule timers in the system itself. And because the sequencer's on a busy duty cycle, it can work at very low granularity, down to nanoseconds if necessary. And from here, we've decided to offer a simple API, where if you want to schedule a timer, for example, place an order into a system, you know that if it's not matched within a given period of time, it must be canceled. So we can just tell the cluster to schedule a timer. And we provide a correlation ID for that timer. It's just an opaque identifier for it and a deadline at which that timer should expire. So it could be just based upon the current time that we currently have in the cluster. Then when that timer expires, it'll call back with an on-time event. And from there, we don't need to manage time inside the cluster. We've got a nice implementation of a timer wheel. We can store lots of these things very efficiently and process them very efficiently, including canceling them, because most timers are canceled before they ever expire. So that has to be an order one, nice, efficient implementation. So we offer that. The really interesting one is the complexities you get with back pressure and how you deal with work. So if you're in a system and you've got a load of clients sending you data in and you're going to pass data on to do something, you take data off an input and you go to send it to the other side. What if the other side isn't ready to deal with it? You're now stuck with this data. So I've read data off a socket and then got to write it to another socket or write it to disk, but it's too busy. What do I do? Do I stash this somewhere? Do I put it in a temporary variable? Do I copy it? It becomes quite a difficult thing. So we want to look at this as a first-class concern. So this is an example of real code from a handler inside the system that deals with our ingress of traffic. So I put the whole thing on the screen because this is it. And it'll actually fit on one slide. So I've got a session message coming into a system. I've got to decide, what am I going to do with this? So first thing I want to check is, do I have a registered session for this? Is this just some bogus data I've got? Well, if the session's already been closed or it's just a bogus thing, I can return out of this with a given status. And the status here is an action to continue. And our continue action means you've consumed this data, continue processing over it, but don't do anything with it at that stage. If that's not the case, it's actually something that you have. So this is a real valid session. Well, let's check now if it's open. And if it's open, I'm going to append it to the log. And appending to the log may apply back pressure, but it may also succeed. If it succeeds in this case, we go into the block. And we're going to update the activity of that client the same way we last did. And we'll return from this with the continue operation again. Now, the very last section is quite simple. So if I haven't skipped over it and I haven't processed it, I haven't been able to do with them. So I want this message to stay around. We return an abort. And that stays in the incoming data structure. We don't need to temporarily store it anywhere else. It's there. And the next time we come in, we can just consume it again without requiring any temporary state. So just thinking about the flows through a system, that you shouldn't have all of this extra states to deal with. Now, what about logs and snapshots? Do we need a distributed file system? Like, we're going to record logs over time. If you've got a system like this, you need to take snapshots occasionally, otherwise you'd have to replay the logs from the beginning of time. So would you open a file and you write all this data to disk on inside the file? How do I get that to another node? How do I read it remotely? Like, we end up with, do you need a distributed file system? We allow the recording of those streams just to be a stream of messages. And we write them down to that stream, and that can then be read remotely. So we effectively get into the ability to have a distributed file system that's pretty fast. Now, how fast is pretty fast? Aeron can easily max a 10 gig E network. if you have a fast enough SSD, we can run at up to about 2 gigabytes, not gigabits, 2 gigabytes per second read and replay of these given streams. So it kind of runs quite nice. We can also process these streams. Again, this is going back to applying some functional principles. We can have multiple services dealing with the same streams. So we've got our case here. We've got our various services consuming this. Why not just have multiple services running off the same thing? Actually piggyback all the same infrastructure. So for example, I've got something doing order matching. What if I want to do risk on the same time? What if I want to do market surveillance? All of these things can run off it completely in parallel and virtually no extra cost. So kind of one last little bit of NIO pain. Inside here, we've got byte buffers. And we've got map byte buffer and direct byte buffer. I guess some people may or may not be familiar with these. So a direct byte buffer is one that's not managed by the garbage collector on the Java heap. It's off heap. It's usually allocated through the likes of Moloch that's under there. And we can use that for sending data to network or to disk. We need those because we can't use normal heap-based data structures for that because they could be moved by the garbage collector as we're actually using them. So we have to use these off-heap structures. We also have memory map files. And memory map files are a really nice feature, but they've got some additional stuff. So I can force a memory map file to disk. I can do some other stuff with it. I mentioned at the start some of the people who worked on some of these consensus algorithms. One of those people is Barbara Liskov, who did a lot of the nice work on VStamp replication. Most people are not aware that she did that. They're more familiar with her input to the solid principles, including Liskov's substitution principle. So under Liskov's substitution principle, I should be able to, if I have one class subclass as another one, I should be able to substitute any subclass for the base class because it should behave exactly the right way. Now, these two classes, one of them subclasses the other. Which would be the right way around to do this? So should it be side 1 where byte buffer will come under a map byte buffer, or should it be side 2 where a map byte buffer should come under a direct byte buffer? Who's for side 1? Good, so most people would not fail Object-Oriented 101 at university. Who's for side 2? Which one do you think is really implemented? We're actually implemented on 1. So the people who give us this would have failed Object-Oriented 101 on any basic computer science course. They put them the wrong way around, and this breaks Liskov's substitution principle. So I'm just about out of time now, so quickly in closing, where are we at? What's the roadmap? We have a working implementation of this. We're just finishing up some of the interesting features around cluster catch-up, where a node leaves the cluster and comes back in again and has fallen behind state. It's looking quite interesting. I remember the first time I talked about Aeron, I used this T-shirt as one of the slides at the end because it's been such a cool thing to work on. And I think the cluster stuff that we're currently working on now is kind of equally as cool as some of the base implementation, because we're finding we can do these things very efficient in kind of quite a nice, fun way. And on that, I'll say thank you very much, and I think I'm out of time.